Welcome to the Whispering Galaxy, where we drift gently through the cosmos, one mystery at a time. Tonight, as you settle into your favorite spot and let the weight of the day slowly dissolve away, we're embarking on a journey into one of the universe's most enigmatic secrets. Something that surrounds us, shapes everything we see, yet remains completely invisible to our eyes. It's the hidden foundation upon which all cosmic architecture rests. Before we begin our quiet exploration, I'd love to know where you're listening from tonight. Are you tucked beneath warm blankets in London as midnight approaches? Perhaps you're watching from a cozy corner in Tokyo as dawn gently breaks. Let me know in the comments below. It's always wonderful to see the cosmos connects how curiosity about us across continents and time zones. If you're new to this channel, welcome home. Consider giving this video a gentle thumbs up and subscribing for more peaceful journeys through space and time. To our returning stargazers, thank you for being part of this quiet community. Your presence makes these nocturnal voyages all the more meaningful. I hope tonight's exploration won't keep you too alert. But if it does, at least you'll drift off knowing something profound about the invisible forces that govern our universe. So take a deep breath, let your shoulders relax, and prepare to discover why the darkness between stars isn't empty at all, but filled with something extraordinary that we're only just beginning to understand. Picture yourself standing in a vast cathedral at twilight. The air is stilled chaff. Ants of fading light filter through ancient windows, illuminating floating particles of dust. But what captivates you isn't the light itself, it's the spaces between those golden beams. The darkness that gives the light meaning, that provides the canvas upon which beauty can unfold. This is perhaps the closest earthly analogy to understanding our universe's greatest mystery. For most of human history, we've gazed upward and seen a cosmos painted in light. Brilliant stars scattered like diamonds across black velvet, spiral galaxies spinning their luminous arms through space, nebulae glowing in ethereal colors that seem almost too beautiful to be real. We built our understanding of the universe around what we could see, touch, and measure directly. But the universe, as it turns out, has been keeping its greatest secret hidden in plain sight. What we see, all those magnificent stars and swirling galaxies, represents only a tiny fraction of what actually exists. It's like admiring the foam on ocean waves while remaining completely unaware of the vast depths beneath. The story begins in the early decades of the 20th century, when astronomers first started noticing something peculiar about the way galaxies moved. They were spinning too fast. Stars at the edges of these cosmic pinwheels should have been flung out into the void long ago, scattered by centrifugal force like water drops flying off a spinning wheel. Yet there they were, serenely orbiting their galactic centers, as if held in place by an invisible hand. At first, scientists assumed they were missing something obvious. Perhaps there were vast clouds of cold gas lurking between the stars, or populations of dim objects too faint for their telescopes to detect. Maybe brown dwarfs, those failed stars that never quite ignited, were scattered throughout space in numbers far greater than anyone imagined. But as observations became more precise and telescopes more sensitive, these explanations crumbled one by one. The universe seemed determined to keep its secret, revealing only tantalizing clues that something vast and invisible was orchestrating the cosmic dance. This invisible something doesn't shine, doesn't reflect light, and doesn't interact with ordinary matter in ways we can directly observe. It passes through planets, stars, and even our own bodies, as if we weren't there at all. Yet its gravitational influence shapes the largest structures in the universe, guiding the formation of galaxies and determining the fate of cosmic evolution itself. Scientists have given this mysterious substance a name that perfectly captures both its importance and its elusiveness. They call it dark matter, though the word dark doesn't quite do it justice. It's not dark in the way a shadow is dark, blocked from light by some obstacle. It's transparent to light entirely, existing in a realm parallel to our luminous world, yet fundamentally separate from it. To understand just how profound this discovery is, imagine learning that your house, which you thought was built of wood and brick, is actually supported by an invisible framework made of something you've never encountered before. The walls you can see and touch are real, but they're held up by a structure composed of materials that exist beyond your senses. That invisible framework doesn't just support your house, it determines its shape, its stability, and its very existence. This is the situation we find ourselves in when we look at the cosmos. Every galaxy, every star, every planet exists within vast halos of dark matter. These halos extend far beyond the visible edges of galaxies, creating gravitational wells that capture and hold ordinary matter, allowing it to cool, condense, and eventually form the stars we see twinkling in the night sky. The more scientists have studied this invisible realm, the more central it appears to be to the story of everything. Without dark matter, the early universe would have remained a thin, nearly uniform soup of particles and radiation. There would have been no seeds around which matter could gather, no gravitational scaffolding to support the formation of the first stars. In a very real sense, dark matter is the universe's architect. It drew the blueprints for cosmic structure, laying out the patterns that ordinary matter would eventually follow. The beautiful spiral arms of galaxies, the intricate web of filaments connecting galaxy clusters, the vast voids that separate these luminous islands, all of these features trace their origins back to the invisible scaffolding of dark matter. Yet, for all its cosmic importance, dark matter remains profoundly mysterious. We know it's there because we can see its effects, the way it bends light around massive galaxy clusters, the manner in which it influences the motion of stars and gas. But we don't know what it's made of. We don't understand how it formed, or why it interacts so weakly with the matter we're familiar with. Some of the most brilliant minds in physics have proposed candidates for what dark matter might be. Perhaps it consists of exotic particles left over from the universe's earliest moments, relics of a time when the cosmos was hot and dense beyond imagination. These particles might be drifting through space right now, passing through your body by the trillions every second without leaving the slightest trace. Other theories suggest dark matter could be composed of axions, hypothetical particles so light and ethereal they would behave more like waves than discrete objects. Or perhaps the answer lies in sterile neutrinos, ghostly cousins of particles we already know exist, but ones that interact even more weakly with ordinary matter. Deep underground, in laboratories carved out of solid rock and shielded from cosmic radiation, sensitive detectors wait patiently for one of these dark matter particles to reveal itself. They listen for the faintest whisper, the tiniest collision that might announce the presence of this invisible realm. So far, the silence has been profound, but the search continues with unwavering dedication. High above our atmosphere, space telescopes map the subtle distortions that dark matter creates in the light from distant galaxies. Like looking at the world through water, these gravitational lenses reveal the presence of massive, invisible structures scattered throughout the cosmos. Each observation adds another piece to a puzzle that grows more intriguing with every new discovery. The implications of dark matter's existence extend far beyond astronomy. If most of the universe is composed of something we've never directly detected, what does that say about the nature of reality itself? How much of existence operates according to rules we haven't discovered yet? There's something both humbling and wondrous about living in a universe where the majority of everything remains hidden from our direct perception. It reminds us that science is not about conquering the unknown, but about learning to listen more carefully to what the cosmos is trying to tell us. As we continue our journey together through the coming segments, we'll explore how this invisible matter reveals itself through the graceful dance of galaxies. Investigate the underground laboratories where scientists hunt for dark matter particles and discover how this mysterious substance may hold the key to understanding the universe's ultimate fate. For now, let yourself rest in the knowledge that you exist within something far grander and more mysterious than the eye alone can perceive. The darkness between the stars isn't empty space, but a rich, structured realm that connects everything in ways we're only beginning to understand. The story of how we first glimpse this hidden universe begins with a Swiss astronomer whose sharp mind matched his equally sharp tongue. In the 1930s, Fritz Zwicky turned his attention to a distant collection of galaxies called the Coma Cluster. What he discovered there would challenge everything astronomers thought they knew about the cosmos. Picture a vast city of galaxies, thousands of them, each containing billions of stars, all bound together by gravity in a cosmic metropolis floating through the depths of space. Zwicky measured how fast these galactic citizens were moving within their celestial city, and what he found made no sense according to the physics of his time. The galaxies were racing around far too quickly. According to Newton's laws, they should have escaped their gravitational bonds long ago, scattered into the cosmic wilderness like leaves blown from a tree in a hurricane. Yet there they were, serenely orbiting within the cluster as if held by invisible chains. Zwicky's calculations revealed something extraordinary. The cluster appeared to weigh hundreds of times more than what all its visible stars and gas could account for. It was as if he were trying to weigh a person by looking only at their shadow, finding that the shadow suggested someone far more massive than what his eyes could see. Being a practical man with little patience for mystery, Zwicky coined a term for this missing ingredient. He called it dunkel Materie, dark matter. The name wasn't meant to be poetic or profound. It was simply the most straightforward description he could offer for whatever invisible something was holding everything together. His discovery was met with the kind of polite skepticism that often greets revolutionary ideas in science. Perhaps there was an error in the measurements. Maybe the light from such distant galaxies was being distorted in ways they didn't yet understand. It seemed easier to assume that the problem lay in the data rather than accepting that the universe might be fundamentally different from what they imagined. But Zwicky's mathematics were stubborn and unforgiving. The numbers told the same story no matter how many times he checked them. Something unseen was providing most of the cluster's gravitational pull, something that didn't shine or reflect light, yet commanded the motion of entire galaxies with its invisible presence. Decades would pass before other astronomers began to notice similar patterns elsewhere. The whisper that Zwicky first heard in the Coma Cluster would eventually become a chorus echoing from every corner of the observable universe. During those intervening years, astronomy underwent its own quiet revolution. Telescopes grew larger and more sensitive, allowing scientists to peer deeper into space and further back in time. Among those pushing the boundaries of observation was Vera Rubin, a meticulous researcher whose gentle persistence would transform our understanding of how galaxies behave. Rubin focused her attention on spiral galaxies, those graceful cosmic pinwheels that spin slowly through space like enormous celestial flowers. She wanted to understand something seemingly simple: how fast different parts of these galaxies rotated around their centers. The expectation was straightforward. Just as planets in our solar system follow a predictable pattern, with Mercury racing around the Sun while distant Neptune crawls along its orbital path, stars in a galaxy should move faster near the center and slower toward the edges. The farther you travel from the gravitational heart of the system, the weaker the pull becomes. But when Rubin began measuring the actual velocities of stars at various distances from galactic centers, the universe once again refused to follow the script. Instead of the expected decline in speed toward the outer regions, she found something remarkable. Stars at the edges of galaxies were moving just as fast as those near the center, as if some invisible hand was keeping the entire cosmic wheel spinning at a uniform rate. Galaxy, after galaxy revealed the same pattern. The rotation curves, those graphs showing how orbital speed changes with distance, didn't drop off as expected. They flattened out, stretching horizontally across her charts, in defiance of gravitational logic. It was as if these cosmic structures had decided to ignore the fundamental laws that governed planetary motion. According to everything astronomers understood about gravity, these galaxies should have torn themselves apart eons ago. The visible matter, all the stars and glowing gas clouds that telescopes could detect, simply wasn't massive enough to hold the outer regions in their steady orbits. Yet there the stars remained, circling peacefully in their appointed paths. Rubin's discovery wasn't limited to a few peculiar galaxies. As her survey expanded to include dozens, then hundreds of these cosmic structures, the same impossible pattern emerged again and again. Something invisible was adding tremendous mass to every galaxy she studied, creating vast halos of unseen matter that extended far beyond the visible edges. These dark matter halos weren't just slightly more massive than the visible components. They outweighed everything that could be seen by factors of 5, 10, or even 20 to 1. It was as if each luminous galaxy was merely the tip of an enormous invisible iceberg floating in the cosmic ocean. The implications were staggering. If every galaxy needed such a massive dark matter halo to remain stable, then the universe was suddenly a very different place than anyone had imagined. The bright stars and colourful nebulae that filled astronomy textbooks represented only a small fraction of what actually existed. The cosmos was dominated by something that couldn't be photographed, couldn't be studied directly, yet was essential to the existence of everything else. Rubin approached these revolutionary findings with characteristic scientific caution. She didn't claim to understand what this invisible matter might be, only that it had to be there. Her careful measurements and methodical approach gradually convinced the astronomical community that they were facing a genuine mystery rather than an experimental error. The beauty of Rubin's work lay not just in its precision, but in its persistence. She continued studying galaxy after galaxy, building an irrefutable case that flat rotation curves were a universal phenomenon rather than an isolated curiosity. Each new observation strengthened the evidence for dark matter's existence while deepening the mystery of its nature. Her discoveries marked a turning point in cosmology. The universe was no longer a place where light revealed all secrets. Instead, it had become a realm where the most important truths remained hidden in shadows, influencing everything while revealing nothing about themselves. As word of these findings spread through the scientific community, physicists and astronomers found themselves confronting a humbling realization. Despite centuries of progress in understanding the cosmos, they had been studying only the most obvious and accessible parts of reality. The universe's true architecture was written in invisible ink, detectable only through its gravitational effects on the small portion of matter that happened to shine. This invisible framework didn't just exist at the edges of galaxies. It formed vast networks connecting distant structures, created the conditions necessary for star formation, and determined the large-scale organization of everything in the cosmos. Every time we looked at the night sky, we were seeing only the decorations hung upon an unseen scaffolding that stretched throughout space and time. The revelation that galaxies were embedded within massive dark matter halos opened an entirely new chapter in our understanding of cosmic architecture. But the mystery deepened when astronomers began to realize that this invisible substance didn't just surround individual galaxies. It connected them across vast distances, weaving an intricate web that spanned the entire observable universe. Imagine standing on a hilltop on a foggy morning, watching the mist slowly lift to reveal a landscape you never knew existed. Where you once saw only empty space, suddenly appear bridges, valleys, and mountain ranges stretching to the horizon. This is what happened to astronomy in the late 20th century as better instruments and computer simulations began to reveal the hidden structure of the cosmos. The universe, it turned out, wasn't a random scattering of galaxies through empty space. Instead, it resembled a vast three-dimensional spider web with luminous galaxies strung like dewdrops along invisible filaments of dark matter. Between these filaments lay enormous voids, cosmic deserts so empty that if you placed our Milky Way in the center of one, you might not encounter another major galaxy for hundreds of millions of light years in any direction. This cosmic web, as scientists came to call it, represented the largest structure in the known universe. The filaments stretched across distances so vast that light takes hundreds of millions of years to travel from one end to the other. Yet despite their immense scale, these dark matter highways are remarkably thin, like cosmic silk threads connecting distant islands of light. To understand how such structure could have formed, we must journey back to the universe's earliest moments. In the beginning, space was filled with an almost perfectly uniform soup of matter and energy. But almost is the key word here. Tiny fluctuations, variations in density of less than 1 part in 100,000, provided the seeds from which all cosmic structure would eventually grow. These primordial ripples were so small, they would have been invisible to any observer. Yet, over billions of years, gravity slowly amplified them, drawing matter toward regions that were even slightly denser than their surroundings. Like snow accumulating in the slight depressions of a field, matter began to collect in these gravitational valleys. Dark matter played the crucial role in this cosmic construction project. Unlike ordinary matter, which was still tangled up with light and radiation in the early universe, dark matter could begin clumping together immediately. It felt only the pull of gravity, ignoring the electromagnetic forces that kept ordinary matter hot and turbulent. As the universe expanded and cooled, dark matter quietly assembled the scaffolding upon which everything else would eventually hang. It formed the first structures, creating gravitational wells that would later capture ordinary matter once it finally decoupled from radiation. When that happened, about 380,000 years after the beginning, gas and dust flowed into these dark matter frameworks like water finding the channels of a riverbed. The result was a universe of stunning complexity and beauty. Dark matter filaments became cosmic highways along which ordinary matter traveled, cooling and condensing as it went. Where multiple filaments intersected, the density became high enough for the first stars to ignite, creating the earliest galaxies in pockets of space that had been prepared for them billions of years in advance. This process continues today. Gas flows along the dark matter web, feeding into galaxies and fueling ongoing star formation. The invisible scaffolding that shaped the early universe still guides the evolution of cosmic structure, determining where new stars will be born and how galaxies will grow over time. Modern computer simulations can recreate this process with remarkable accuracy. Starting with nothing but the laws of gravity and the initial conditions of the early universe, these digital cosmos evolve over billions of simulated years. Dark matter particles, represented by millions of mathematical points, attract each other gravitationally as the virtual universe expands. What emerges from these calculations is breathtaking. The simulated universe develops the same web-like structure we observe in the real cosmos. Filaments form naturally, connecting dense nodes where galaxy clusters eventually appear. Vast voids emerge between the filaments, creating a foam-like pattern that matches what telescopes reveal when they map the positions of millions of galaxies. The agreement between these simulations and observations represents one of the great triumphs of modern cosmology. Using only the assumption that dark matter exists and interacts gravitationally, scientists can reproduce the large-scale structure of the universe with stunning precision. It's as if we've discovered the universe's blueprint, written in the language of invisible matter. But the cosmic web isn't just a static structure frozen in time. It's a dynamic, evolving network where matter continues to flow along the filaments toward the densest regions. Galaxies slide along these dark highways like cars on invisible roads, occasionally colliding and merging when their paths intersect. Even our own Milky Way is travelling along one of these filaments, part of a larger flow of galaxies moving through the cosmic web. The voids between the filaments aren't truly empty, but they're close to it. These cosmic deserts contain less than 1/10 the average density of matter in the universe. They're so underpopulated that an observer placed in the centre of a large void might see no galaxies at all within their cosmic horizon. The night sky would be almost perfectly black, with perhaps only a handful of distant, faint SEM of furudges marking the edges off filaments. Yet even these apparently empty regions play an important role in the cosmic story. The voids provide the negative space that gives structure to the web. Without them, the filaments couldn't exist. They're like the silence between notes in a musical composition, essential to the overall harmony, even though they produce no sound themselves. As we trace the cosmic web from the smallest scales to the largest, we find that dark matter's influence extends everywhere. It shapes the halos around individual galaxies, connects them through vast filaments, and determines the overall architecture of the universe. Every structure we see, from the smallest dwarf galaxy to the largest superclusters, exists because dark matter provided the gravitational foundation upon which it could form. This invisible web also helps explain why galaxies aren't distributed randomly through space. They follow the underlying dark matter structure, clustering along filaments and avoiding the great voids. The pattern of galaxy distribution that we observe today is essentially a fossil record of the dark matter web that formed billions of years ago. Perhaps most remarkably, this same web-like structure appears at every scale we can observe. Galaxy clusters are connected by filaments of dark matter and separated by voids. Individual galaxies within those clusters follow similar patterns. Even the dark matter halos around single galaxies show hints of substructure, smaller streams and clumps that trace their own miniature version of the cosmic web. It's as if the universe has a fractal quality, with similar patterns repeating at different scales. The same gravitational processes that create the largest structures also operate on smaller scales, producing nested hierarchies of dark matter architecture. We exist within this multi-layered framework, inhabitants of a galaxy that sits within a cluster that lies along a filament of the cosmic web. The discovery of this hidden architecture has transformed our understanding of our place in the cosmos. We're not floating in within a vast, invisible network empty space, but in bed that connects us to the most distant reaches of the observable universe. Every atom in our bodies has travelled along these dark matter highways, following paths laid out by gravitational forces acting over cosmic time. As astronomers continue mapping the cosmic web in uncovering new mysteries ever greater detail, they're UNC about how this invisible architecture influences the visible universe. The web appears, an information, creating coral to channel not just matter, but also energy oceans between distant regions that shouldn't be able ongoing exploration, reminds us that even to communicate with each other. This, our grandest discoveries about dark matter, our web may be only the most obvious, likely just the beginning. The cosmic manifestation of dark matter's influence. There could be subtler structures, smaller scales of organization, or entirely different ways that this mysterious substance shapes reality. For now, we can marvel at the elegant simplicity of a universe where invisible threads connect every point of light in the night sky. The cosmic web stands as a testament to the power of gravity to create order from chaos, structure from simplicity, and beauty from the invisible foundations of reality itself. The cosmic web may be the most obvious manifestation of dark matter's architectural influence, but it's far from the only way this invisible substance reveals its presence. Sometimes the universe provides us with natural experiments so dramatic and clear that they serve as cosmic laboratories, allowing us to witness dark matter's behavior in ways that would be impossible to recreate on Earth. One of the most spectacular of these cosmic demonstrations occurred about 150 million years ago, when two massive galaxy clusters collided in a region of space now known as the Bullet Cluster. This collision wasn't a gentle merger, but a cosmic catastrophe of unimaginable proportions, with each cluster traveling at speeds of several thousand kilometers per second when they met. When astronomers first observed the aftermath of this collision, they discovered something that would become one of the most compelling pieces of evidence for dark matter's existence. The hot gas that makes up most of the ordinary matter in galaxy clusters had slammed together during the collision, heating up to temperatures of hundreds of millions of degrees and glowing brilliantly in X-ray wavelengths. But something extraordinary had happened during this cosmic crash. When scientists used gravitational lensing to map where most of the mass actually resided, they found that it hadn't stopped with the gas. Instead, the bulk of each cluster's mass had passed straight through the collision zone, continuing onward as if the crash had barely affected it at all. This created a remarkable separation between light and gravity. The X-ray glow marked where the ordinary matter had collided and heated up, but the gravitational lenses revealed that most of the mass was somewhere else entirely. It was as if two invisible ghosts had passed through each other while their luminous clothing got tangled up in the collision. The implications were profound. Here was direct evidence that most of the matter in these clusters consisted of something that didn't interact with itself or with ordinary matter through any force except gravity. The dark matter components of each cluster had sailed through the collision unimpeded, while the gas and stars got caught up in the electromagnetic chaos of the crash. This behavior perfectly matched what scientists had predicted dark matter should do. Unlike ordinary matter, which can collide, heat up, and slow down through electromagnetic interactions, dark matter particles should be able to pass through each other and through ordinary matter as if neither existed. The Bullet Cluster provided the first clear observational proof that this theoretical property was real. But the Bullet Cluster isn't unique. Astronomers have since discovered dozens of similar collision systems, each one providing another natural laboratory for studying dark matter's properties. Some show even more dramatic separations between the ordinary matter and the gravitational mass, creating cosmic scenes that look almost surreal when viewed through different types of telescopes. These colliding clusters also reveal something important about dark matter's distribution within individual galaxy clusters. The dark matter doesn't form a smooth, uniform halo around each cluster. Instead, it shows structure and clumpiness, suggesting that dark matter halos themselves have internal architecture that we're only beginning to understand. The study of these cosmic collisions has also helped scientists rule out alternative explanations for the phenomena attributed to dark matter. Some theories had suggested that perhaps gravity itself behaves differently on cosmic scales, eliminating the need for invisible matter. But the clean separation between ordinary matter and gravitational effects in colliding clusters is difficult to explain without invoking a separate component of matter that interacts only gravitationally. Beyond these dramatic collisions, dark matter reveals itself through subtler gravitational effects that require extraordinary precision to detect. One of the most elegant of these techniques involves measuring tiny distortions in the shapes of distant galaxies caused by the gravitational influence of dark matter structures lying between them and Earth. This phenomenon, known as weak gravitational lensing, works because massive objects bend the path of light traveling near them. When light from a distant galaxy passes through a region filled with dark matter, its path gets slightly deflected, causing the galaxy's image to appear slightly stretched or distorted when it reaches our telescopes. The effect is incredibly subtle. Individual galaxy distortions are far too small to measure reliably, but by studying the shapes of millions of galaxies and looking for statistical patterns in their distortions, astronomers can create maps of dark matter distribution across vast regions of sky. It's like trying to detect the presence of invisible obstacles by watching how they affect the shadows cast by objects behind them. These weak lensing surveys have revealed dark matter structure in unprecedented detail. They show how dark matter, clumps and filaments connect galaxy clusters across hundreds of millions of light years. They've even detected dark matter structures that contain no visible galaxies at all, pure concentrations of invisible matter lurking in apparently empty regions of space. Perhaps most remarkably, these surveys have allowed scientists to trace how dark matter structure has evolved over cosmic time. By studying galaxies at different distances, and therefore at different stages in the universe's history, astronomers can watch the cosmic web grow and evolve over billions of years. The dark matter scaffolding that was barely perceptible in the early universe has slowly condensed into the intricate network of filaments and nodes we observe today. This evolution of dark matter structure also provides crucial insights into the nature of dark matter particles themselves. Different theoretical candidates for dark matter would produce different patterns of structure formation. By comparing observations with computer simulations, scientists can constrain the properties that dark matter particles must have. The precision of these measurements has reached extraordinary levels. Modern surveys can detect the gravitational influence of dark matter structures that are barely more dense than the average matter density of the universe. They're sensitive enough to map dark matter filaments that are invisible even to the most powerful telescopes, revealing architecture that exists purely in irrational realm. The gravitational archaeology projects have also uncovered evidence of dark matter's role in galaxy formation and evolution. Galaxies don't just sit passively within their dark matter halos. The ongoing accretion of dark matter influences how galaxies grow, how they form stars, and how they interact with their environments. Some of the most intriguing discoveries involve the relationship between a galaxy's visible properties and its dark matter environment. Galaxies in dense dark matter regions tend to be redder and more massive, while those in underdense regions are often bluer and more actively forming stars. This suggests that dark matter doesn't just provide structural support for galaxies, but actively influences their evolution over cosmic time. The study of satellite galaxies has provided another window into dark matter's properties. Small galaxies, orbiting larger ones like our Milky Way, trace out the gravitational field of their host's dark matter halo. By measuring the orbits and distributions of these satellites, astronomers can infer the shape and extent of the invisible matter surrounding us. These measurements have revealed that dark matter halos aren't perfectly spherical. They show evidence of substructure, streams of material, and complex gravitational interactions that speak to a rich dynamical history. Our own galaxy's halo bears the scars of ancient mergers, with streams of disrupted satellite galaxies creating a fossil record of past encounters, written in the language of stellar motions. The precision of these observations has also led to some puzzling discrepancies between theory and observation. Computer simulations predict that dark matter halos should have more small-scale structure than we actually observe. This has led to intense debate about whether our understanding of dark matter physics is incomplete, or whether ordinary matter processes like stellar feedback have modified the dark matter distribution in ways we don't fully appreciate. These tensions between theory and observation remind us that despite decades of progress, dark matter remains profoundly mysterious. We can map its distribution, measure its effects, and constrain its properties, but we still don't know what it actually is. Every new observation brings both answers and new questions, deepening our appreciation for the complexity of this invisible realm. As we've traced dark matter's influence from individual galaxy halos to the cosmic web, we've seen how this mysterious substance serves as the universe's master architect. But perhaps nowhere is its influence more evident than in our own cosmic neighborhood, where we drift unknowingly through an ocean of invisible matter that shapes everything from our galaxy's structure to the very stability of our solar system's orbit around the galactic center. The Milky Way, our cosmic home, appears to us as a gentle river of starlight stretching across the night sky. But this familiar band of light represents only the luminous heart of something far more vast and mysterious. We live within an enormous sphere of dark matter, a halo that extends hundreds of thousands of light years beyond the visible edges of our galaxy, and we're traveling through it right now at tremendous speed. Every second of every day, our solar system races through this invisible ocean at roughly 220 kilometers per second. That's fast enough to circle the entire Earth in less than 3 minutes, yet we feel no wind, no resistance, no indication whatsoever that we're moving through anything at all. The dark matter around us is so ethereal, so disconnected from ordinary physics, that it passes through our planet, through our bodies, through every atom we're made of, without leaving the slightest trace of its passage. To appreciate the scale of this invisible architecture, imagine our galaxy as a glowing coin floating in the center of a vast, transparent sphere. The coin represents everything we can see with our telescopes, all the stars and gas and dust that make up the Milky Way's visible structure. But the sphere itself, stretching far beyond the coin in all directions, represents the dark matter halo that actually defines our galaxy's true extent and mass. This halo isn't uniform or featureless. Like the cosmic web on larger scales, it has structure, streams, and subhalos created by the gravitational remnants of smaller galaxies that our Milky Way has consumed over billions of years. These stellar streams, as astronomers call them, are the visible ghosts of ancient mergers, trails of stars torn from their original homes and stretched into long ribbons that wrap around our galaxy like cosmic scars. The Sagittarius stream is perhaps the most prominent of these gravitational fossils. It's the stretched remains of a dwarf galaxy that ventured too close to the Milky Way and was gradually torn apart by tidal forces. Today, its stars form a faint arc that completely encircles our galaxy, a shimmering reminder of the violent encounters that have shaped our cosmic neighborhood over deep time. By studying these streams, astronomers can map the invisible landscape through which we're traveling. Each stream follows a path determined by the dark matter's gravitational field, curving and twisting according to the hidden topography of our halo. It's like tracking the course of a river to understand the shape of the land it flows through. Except here, the rivers are made of stars and the landscape is composed of invisible matter. Recent discoveries have revealed that our local dark matter environment is even more complex than previously imagined. The Milky Way and its neighbour, the Andromeda Galaxy, are both embedded within an even larger structure called the local group, a collection of galaxies bound together by their mutual gravitational attraction. But beyond that lies something even more vast and mysterious. Our local group is part of an enormous supercluster called Laniakea, a gravitational watershed that spans more than 500 million light-years and contains the mass of 100 quadrillion suns. The name means immense heaven in Hawaiian, and it represents one of the largest coherent structures ever identified in the observable universe. We're not just drifting randomly through space. We're following invisible currents in this vast dark matter ocean, carried along by gravitational flows that connect us to distant galaxies we'll never see. This motion through the dark matter sea has profound implications for experiments designed to detect these invisible particles. As our solar system orbits the galactic center, it should create a kind of dark matter wind, a preferential direction from which these particles approach Earth. This wind changes throughout the year as our planet orbits the Sun, creating seasonal variations that might be detectable by sufficiently sensitive instruments. Underground laboratories around the world are tuned to listen for these subtle signals. Deep beneath mountains and former mine shafts, surrounded by tons of rock that filter out cosmic rays and other background radiation, extremely sensitive detectors wait patiently for the whisper-soft collision of a dark matter particle with ordinary matter. These experiments represent some of the most challenging measurements ever attempted in physics. The expected signal is incredibly weak, perhaps one collision per day in a detector containing several tons of target material. It's like trying to hear a single raindrop falling on a roof during a thunderstorm. Except the thunderstorm never stops, and the raindrop might not fall for months or years. The detectors themselves are marvels of precision engineering. Some use liquid xenon cooled to extreme temperatures, where even the faintest energy deposit can create a tiny flash of light. Others employ crystalline materials so pure and so cold that the slightest vibration from a particle collision can be measured as a minute temperature change. These instruments are so sensitive they can detect the passage of individual cosmic ray particles, the decay of single radioactive atoms, even the gravitational waves from distant black hole mergers. Yet despite decades of increasingly sophisticated searches, the dark matter particles continue to elude direct detection. Each null result narrows the range of possibilities, ruling out certain masses and interaction strengths. But the fundamental mystery remains unsolved. The particles that make up most of our galaxy's mass remain as ghostly and intangible as ever. Some scientists have begun to wonder whether dark matter might be even stranger than we imagined. Perhaps it exists in a completely separate sector of physics, interacting with itself through forces we know nothing about. Maybe it forms its own complex structures, dark atoms and dark molecules that create an entire shadow chemistry invisible to our instruments. There could be dark stars and dark planets, an entire dark ecosystem operating parallel to our own, but forever beyond our ability to observe directly. Other researchers are exploring the possibility that dark matter might not be made of particles at all, but could be more exotic. Perhaps instead be something even it consists of primordial black holes, objects formed in the universe's earliest moments that are too small to be detected individually, but collectively provide the missing mass. Or maybe it's composed of cosmic strings, one-dimensional defects in space-time left over from the universe's infancy. The search for dark matter has also expanded beyond Earth. Space-based detectors look for the high-energy radiation that might be produced when dark matter particles collide and annihilate each other. These cosmic ray experiments scan the sky for unexpected sources of gamma rays, positrons, or neutrinos that could betray the presence of dark matter reactions in regions where this invisible substance is most concentrated. The center of our galaxy, where dark matter should be densest, has become a particular focus of these indirect searches. Several space telescopes have detected an excess of gamma ray emission from this region that doesn't quite match the expected signals from known astrophysical sources. For a while, this mysterious glow looked like it could be the long-sought signature of dark matter annihilation. But alternative explanations involving undiscovered populations of pulsars or other exotic objects have made the interpretation uncertain. Even if we never succeed in detecting dark matter particles directly, the search itself has already transformed our understanding of the universe and our place within it. We've learned that we live within a vast, invisible ocean that connects us to the largest structures in the cosmos. Every breath we take, every step we make, occurs within a medium that shapes the destiny of galaxies and determines the architecture of reality itself. The dark matter halo surrounding our galaxy isn't just a passive container for the stars we see. It's an active participant in our cosmic story, influencing everything from the rate at which new stars form to the eventual fate of our galactic home. In roughly 4 billion years, when the Milky Way and Andromeda galaxies finally merge, it will be their dark matter halos that lead the dance, their invisible masses drawing the visible galaxies together in a cosmic waltz that will reshape our corner of the universe. As we continue our journey through this invisible realm, carried along by currents we cannot see or feel, we remain connected to every other structure in the observable universe through the dark matter web that binds everything together. We're not isolated observers looking out at a distant cosmos, but integral parts of a vast interconnected system where the seen and unseen work together to create the magnificent tapestry of existence we call home. The quest to understand what dark matter actually is has led scientists down some of the most intriguing theoretical paths in modern physics. Deep in underground laboratories and high-energy particle accelerators, researchers are hunting for clues that might finally reveal the identity of this cosmic phantom shapes everything, yet that touches nothing. The leading candidates for dark matter particles read like a cast of characters from science fiction, each with its own peculiar properties and theoretical justification. The most popular among them are called WIMPs, an acronym that stands for Weakly Interacting Massive Particles. Despite their humble name, these hypothetical particles could solve one of the universe's greatest mysteries. WIMPs would be relics from the universe's earliest moments, created in the primordial furnace when space was hot and dense beyond imagination. As the cosmos expanded and cooled, most of these particles would have annihilated each other in bursts of energy, but a small fraction could have survived, becoming the invisible scaffolding we observe today. They would be heavy compared to the particles we know, perhaps 100 times more massive than a proton, yet they would interact so weakly with ordinary matter that trillions could pass through your body every second without you ever noticing. The appeal of WIMPs lies in their elegant simplicity. They emerge naturally from extensions of our current understanding of particle physics that attempt, particularly, theories to unify the fundamental forces of nature. In these frameworks, every known particle has a heavier, more elusive partner, and the lightest of these partners would be stable enough to persist since the beginning of time. But WIMPs aren't the only possibility. Another candidate comes from an entirely different corner of theoretical physics. Axions are particles so light and ethereal they would behave more like waves than discrete objects, permeating space like an invisible fog. Originally proposed to solve an obscure problem in quantum field theory, these ghostly entities could collectively account for all the dark matter in the universe through sheer numbers rather than individual mass. If axions exist, they would be produced not through violent collisions, but through the gentle oscillations of quantum fields that fill empty space. They would be born constantly, everywhere, as the vacuum itself, vibceptible energy. These parrots with barely particles would be so weakly interacting that they could pass through entire planets as if they were made of gossamer, occasionally converting into photons when they encounter strong magnetic fields. Scientists have built ingenious devices to catch this conversion in action. These axion detectors consist of powerful magnets surrounding empty cavities, tuned to resonate at specific frequencies, where axions might reveal themselves by transforming into detectable light. The experiments require extraordinary patience, as researchers adjust their instruments across vast ranges of possible axion masses, listening for whispers so faint they would make a butterfly's footsteps sound like thunder. A third possibility ventures even further into the exotic. Sterile neutrinos would be cousins of the ghostly particles we already know exist, but ones that interact even more weakly with ordinary matter. Regular neutrinos are already among the most elusive particles in physics, capable of traveling through light years of solid lead without being stopped. Their sterile counterparts would be even more aloof, participating only in gravitational interactions while ignoring all other forces entirely. These sterile neutrinos could have been produced in the early universe through quantum processes, so subtle we're only beginning to understand them. They would be warm rather than cold dark matter, moving at speeds that could smooth out the smallest structures while still allowing larger ones to form. Some observations hint at their presence through tiny anomalies in the cosmic microwave background and the behavior of galaxy clusters, though the evidence remains tantalizingly ambiguous. Each of these candidates represents a different vision of what the invisible universe might contain. WIMPs suggest a cosmos filled with heavy, sparse particles drifting through space like cosmic boulders. Axions paint a picture of reality permeated by light, numerous entities forming a kind of quantum mist. Sterile neutrinos offer something in between, particles that bridge the gap between the matter we know and the mystery we're trying to solve. The experimental search for these particles has pushed technology to its absolute limits. Deep underground, shielded from cosmic radiation by miles of solid rock, detectors wait in cathedral-like chambers carved from ancient stone. These instruments are cooled to temperatures colder than interstellar space, surrounded by layers of purified materials, and monitored by sensors so sensitive they can detect the recoil of a single atomic nucleus struck by an invisible visitor from the dark sector. The silence from these experiments has been both frustrating and illuminating. Each year that passes without a detection narrows the theoretical possibilities, ruling out certain masses and interaction strengths with increasing precision. The non-discovery of dark matter particles is itself a form of discovery, teaching us about the limits of what these mysterious entities can be. Meanwhile, particle accelerators are attempting to create dark matter in controlled collisions, smashing protons together at energies that recreate conditions from the universe's first moments. If dark matter particles can be produced in these artificial Big Bangs, they would carry away energy from the collision, leaving behind a signature of missing momentum that sophisticated detectors might be able to measure. The Large 27 Hadron Collider, that kilometre ring of superconducting magnets buried beneath the Swiss-French border, has become humanity's most ambitious dark matter factory. In the fraction of a second following each collision, detectors record the shower of particles that spray outward, accounting for every fragment with meticulous precision. When the energy doesn't balance perfectly, when something appears to have vanished without explanation, physicists lean forward in their chairs and wonder if they've glimpsed the shadow of the invisible realm. As we reach the end of our gentle journey through the invisible cosmos, remember that you exist within something far more mysterious and beautiful than the stars alone can reveal. The darkness between galaxies isn't empty silence, but a rich, structured realm humming with invisible threads that connect every point of light in the night sky. Whether dark matter reveals itself tomorrow or remains hidden for generations to come, its quiet presence continues to shape our cosmic home, holding everything together in ways we're only beginning to understand. Until our next voyage through the whispering cosmos, rest peacefully knowing you drift through an ocean of wonder that stretches beyond sight, carried by invisible currents in the grand architecture of existence itself.